Dear students, today let us solve a problem. See, the problem is given like this. Determine the smallest size of the punch that can be made to punch 10 millimeter thick mild steel plate having ultimate shear stress as 0.3 kilonewton per mm square. The permissible crushing stress for the hardened punch is 1.3 kilonewton per mm square. Okay, now you come here. Here there is a diagram. See, there is a plate in the top view. It is shown like this. A plate is there. In the middle of that, a hole is to be made. How will you make this hole? See, this is that plate. Now what is this down one? This down one is one table on which this plate is kept, and there is that also has a hole because that punched piece should fall off. That's why. Okay, so this is the plate. This is the plate. What plate? MS plate. MS plate means what? Mild steel plate. Okay, and it has a thickness T, and in that we have to make a, a hole. We have to punch a hole, and whose diameter is given by small d. Okay, how will you make it? You bring one equipment called as punch, and this punch has diameter d and it is circular. How will you know that? How do you know that this is circular? By what type of break it is having. If it is broken like this, then that means it is circular. Okay, a circular hole. The circular punch is here, and if you bring it with much force, with hammer force, and pierce through this or punch through this, see, it will cut like this, and this piece, this cylindrical piece will fall off. Okay, then what you are left with is a punched sheet or punched plate. Okay, so now here there are two things. One thing is your punch may fail. How punch will fail? Suppose you are hitting it against this surface, and this surface is very hard, that it cannot be made into hole, or it cannot be you cannot do anything to this surface. Then what? This thing may get crushed off. Suppose this is made of um, banana. Okay, and you hit against this, what will happen to the banana? Banana will get crushed, and it will, the material will go this side and this side. Okay, so that is called as crushing failure. It is failing in crushing. Suppose this material of the punch is very soft and this plate is very hard, then this punch cannot make a hole here. You see, for making a hole, that's why tools, this is a tool, punch is a tool. This tools, any tool should be much harder compared to the workpiece. This is the workpiece and this is the tool. Okay, this workpiece should be softer compared to the tool. Okay, that means what? This punch is hardened. Why heat treatment is done? How do you harden it? By heat treatment. Why heat treatment is done? Because everything that is a tool should be hard. So to become hard, we harden it. We do heat treatment, and this is soft. Okay, so uh, now what is happening is, you see, this one thing is, this punch may fail in crushing. It can get crushed. What did we say? Crushing stress. Crushing stress we studied before. You see, wherever this point is, this thing is coming in contact with the other thing, in that surface the failure takes place. Crushing stress is a localized stress. It is not there in the entire body. Okay, only here where it is coming in contact. Okay, and the second thing is, if this punch is very hard and this is soft, then if you just pierce it through this, then what? Or punch through it, because this is softer material, this much portion will just cut and fall off. Okay, so see, what is that property? which in which this should be weak for this hole to be formed. See, this much thing, actually it is a cylindrical, it is a circular. Okay, in front view you are seeing it as a rectangle, but when you see on the top view, it will be looking like a circle like this. Okay, this falling off piece. Okay, now this thing should be cut. Where it should be cut? Where is cutting taking place? At the circumference. Cutting is taking place. And for how much length it is taking place? For the entire thickness of this plate. That means what? You are cutting along this line. What is the length of this line? Length of this line is the circumference. What is the circumference? Circumference is given by the formula pi d. Pi is 3.14 and d is the diameter. So this is almost 3 times or 3.14 times exactly of the diameter. Okay, so 3.14 times the length and thickness is t. So now you see, if this is failing, if the punch is failing, it is failing at this contact area. And what is the contact area? Pi by 4d square. If this is shearing, shearing means it is cutting off. When this is shearing, it is shearing at the area pi d and into t. Okay, pi dt will be the shearing area. I hope you understood. Now coming to the problem. What is the data given? Data given is, see, 10 mm thick mild steel plate. The thickness is 10 mm. Okay, and is ultimate shear stress is 0.3 kilonewton per mm square. This shear stress is of which material? Now we are having two materials. One is sponge and one is the plate. This here it is mentioned. Mild steel plate having ultimate stress of this. Okay, ultimate stress means shear ultimate what stress? Shear stress. T shear stress is given by tau and tau s, and because it is ultimate you put u also. Tau su is 0.3 kilonewton per mm square. Okay, so that is that kilo, if you remove kilo, it becomes 0.3 into 10 to the power cube. Kilo is 10,000, that is 10 cube newton per mm square. Okay, this is the strength in shear strength of the plate. Now another stress is given here, the permissible crushing stress. For which material? This is for the punch material. This is not for the plate. This is for the plate and this is for the punch. So what is crushing stress? So crushing stress is sigma c. I told you before and again I am telling you that shear stresses are given by the letter tau, whereas all the other stresses are given by sigma. Direct stresses are given by sigma. Shear stress is given by tau. And this is crushing stress, so sigma c. C stands for crushing. Sigma c is what? 1.3 kilonewton per mm square. What that is? 1.3 into 10 to the power 3 newton per mm square. Okay, this much you understood. Now the next question. Is, you see, what is the question actually? Determine the smallest size of the punch. See, the size of the punch means the diameter of the punch. D you have to find out. Okay, for the smallest size of the punch, you see, there are two dimensions. In this figure, there are two dimensions. One is this T, another is this D. See, T, actually how much is this rectangle is immaterial. It can be extending this side how much ever length and this side how much ever length, that side how much ever, this side how much. What we are interested is only in the hole that is being punched here. So this dimension T is known, this diameter D is not known. That's what we have to find out. So now what we are doing is, first you find out what is the maximum shear force that is required to punch a hole. See, when will a hole be punched? If the force is more than the shear force, maximum shear force. So what is the shear force? Shear force, is the how much, see, you know that stress is load upon area. Otherwise, load is equal to area into stress. Okay, shear area into the ultimate shear stress. That will be the shear load. So this is shear area. I already told you the area will be pi dt. Every time in such problems, what is important is to first find out what is the area, resisting area or failure area. That is what you have to find out. Here, because you have to make hole in the circle on the periphery and to a depth of t, so the circumference is pi d and thickness is t, so the pi dt will be the area of that plate which is shearing, for the hole which is shearing, and it has an ultimate shear stress of tau s2 su. Okay, so we know pi and d we don't know, and su we know, it is given, so we put in this formula, and this comes to because we don't know d, this comes in terms of d. So ps is equal to 9424.78 d. You calculate and see so much value is coming or not, so many newtons. Okay, this is equation 1. Now next coming to the, first we thought about the plate, now next coming to the punch. Now, what is the area of failure here? This is pi by 4 d square because it is circular in cross section. Okay. And what is the permissible crushing stress? That is sigma c. So, what is the maximum crushing force? Maximum crushing force on the punch that will be coming is, say, P is the load. See, force and load they will be alternately using. So, P suffix C, that is crushing load, is equal to crushing area into permissible stress. You see here again, stress is equal to load upon area. So load upon crushing area will be stress. So if we are rearranging, load will become crushing area into permissible stress. Okay, so crushing area pi by 4 d square and permissible crushing stress is sigma c. And here also we know all the other terms, only d is not known. So now we get this term in terms of d square. So PC is equal to 1021.017 d square, so many newtons. Okay, when you calculate and see whether this is coming. Okay, now to find out what is the minimum diameter or minimum size of the punch that can be done, so we have to equate these two equations. First we got one equation, this is the second equation. Now equating these two, that is PC is equal to PS. So one side you will have d square, the other side d, and from this you will find out this diameter. So what you have done is you have found out what is the maximum crushing stress that this can withstand, and what is the maximum crushing force that this can withstand. Then for this, what is the maximum shear load that it can withstand, and we are equating those two and we are finding out the diameter. That is how you have to solve this problem. This problem is asked many times in the exam. So if any problem, you can contact me through Google Classroom or in WhatsApp also. I'll be able to answer. Okay, next another problem here we are having. Two plates 20 mm thick are joined by a double riveted lap joint. See, this is one plate and its thickness is 20 mm. This is another plate whose thickness is 20 mm. They are joined by double riveted joints. That means there are two holes here. 20 mm thick, that means 2 centimeters. This plate must be very big, very thick. And this next what they are saying, the rivets are 30 mm in diameter. 30 mm diameter means this thickness is 30. This diameter is 30. This diameter 30 diameter means what? 3 centimeters. 3 centimeters hole means it's a very big hole, and these rivets are big. This must be used for very a big application. Very heavy. You think of it, 20 mm thick mild steel plate, how heavy it will be. Okay, anyway, now what is the question? For crushing stress induced, what type of stress? Crushing stress. You pay attention here. This is crushing stress. It is not shear stress. You see, this rivet can fail in two ways. One is it, if the force is more, it can get crushed, though it can get sheared off here. Now the question is not shearing stress, so we are not considering about cutting off here. Now the question is, find the crushing stress induced. Find the crushing means what? If you are pulling it like this rivet is in the way, this plate will be crushing this rivet. You see, plate is being pulled, rivet is there. So what will happen at this surface? At this surface, crushing will take place, and also again at this surface. Okay, this surface on the upper plate, here and here crushing will take place. In the lower plate, when you are pulling it, so on this surface here and on this surface here, the crushing will take place. Okay. So what they are saying is, find the crushing stress induced with the plate and the rivet if the maximum force is 50 kilonewton is applied. This P is 50 kilonewtons. This force P, this arrow is given there also, it is 50 kilonewtons. Okay. So when we are pulling it like this 50 kilonewtons. 50 kilonewtons means what? K. See, when we are writing units, we write small k like this. Small k stands for kilo. Capital K stands for Kelvin, degree Kelvin. Okay, so you should not write capital K. Always remember, in SI units, capital letters are reserved for the names of the scientists like Newton, Watt, Kelvin, like that. For those are capital letters, whereas small letters are used for all the other things. So kilo you should use small k. Okay, small k means kilo, 1000, or 10 to the power cube, that is 10 to the power 3. That is what is the meaning. Now crushing failure takes place at this surface. So this rivet may fail in crushing at this surface. Shear takes place here, but in this question shear is not asked, so we are not bothered about shear. We are bothered only about crushing. Crushing is taking place here. Crushing is taking place means, what will be the crushing area? Crushing area is the projected area. You see, if you remember the previous lectures, I told you crushing area is the projected area. You see, projected area is, see, this thickness is T, and the other side will be D, the diameter. So pi D into T, D into T, this will be the area of crushing or resisting area, we call it dt. And now there are two rivets here, so N. Okay, so here also it is getting crushed, here also it is getting crushed, so two rivets into the area d into t. Okay, now the crushing stress is sigma c is load upon area. Load is P. This P is capital P, this one, and area is for one rivet dt, for two rivets dt into 2, that is dtn, dt into 2. That is the meaning. Projected area means it is how a cylinder, it is see, rivet is a cylinder in the top view or front view. If you project, what happens? It will look like a rectangle. So rectangle's diameter, rectangle's area is dt. Okay, a cylinder looks a circle in one view and rectangle in two views, if you remember engineering drawing. Okay, so this is the projected area dt. Okay, now substitute the values. 50 into 10 cube upon d is 30, t is 20, and n is number of rivets 2. So you will find out why 10 to the power 3 we have used, because k we have converted into 10 cube. Okay, 41 into 66 Newton per mm square. So this is the crushing stress that is induced. Induced means what? That is coming in the plate as well as the rivet. Okay, coming to the next point, next topic, we come to principal stress and principal strain. You see, if you take one machine component, on that there can be a tensile force, there can be from some other side there can be a compressive load, and also in some other direction a shear load may be coming, or a number of such loads may be coming. It is not that one member is subjected to only one type of stress. Many types of stresses can be coming. So when we are coming so many, when they come, what we do is we have to find out what is the effect of all this. So when we suppose there are two types of stresses, two stresses are coming, two tensile stresses are coming, you see, then what, the two tensile stresses both are in the same direction means you just add them. If two tensile stresses are coming, one is in one direction, the other is the other direction, you for finding out the resultant stress, you have to subtract the smaller one from the bigger one. And similarly, but if there are different types of stresses, one is tensile stress, one is compressive stress, and one is a shear stress, like that, and like that many stresses are coming, what are you going to do? For that you have to find out what is the result stresses. So they have found out, you see here, in a design of machine component, the uniaxial state of stress is rarely used because most of the components are subjected to a combination of loads such as axial load, bending moment, twisting moment, and such things. The biaxial triaxial state of stress is the most common condition on the surface of the component. Is a uniaxial means one axis, biaxial means two axis, triaxial means three axis. Therefore, the designer is to relate the biaxial and triaxial state of stress and strength are achieved are strength to achieve sufficient margin of safety. See, we have to consider how all the stresses. Okay, now let us consider this biaxial stress shown in figure 1.311. I think this is the figure. Okay, this is the figure. This actually you derive in applied mechanics and strength of materials. Okay, you see, suppose there is a direct stress sigma 1 here, there is another direct stress sigma 2 here, and there is this shear stress tau working here, here and here. Okay, so in that case, now what we are saying is, you consider in which shear stress tau is there. This stress is cut in oblique plane, inclined at theta degrees to the x-axis. See, there is an oblique plane, and now this is the x-axis, and this is now this is the x-axis, and this is the theta degrees making with the x-axis. Okay, at any point in the strained material, there are three planes mutually perpendicular to each other which carry direct stresses only and no shear stress. But out of these direct stresses, one will be maximum, the other will be minimum. These perpendicular planes which have no shear stresses are known as principal planes, and the direct stress along these planes are known as principal stresses. See, in short, what they are saying is, in a, in a situation where many stresses are coming, see, we resolve them and find out that there is one particular plane, maybe a plane like this, which is inclined at theta degrees, on which there are only direct stresses present and no shear stress. Okay, there are two, actually, how many okay, how many planes they have said? They have said three planes mutually perpendicular to each other. Three planes are there which are mutually perpendicular to each other, and these perpendicular planes have no shear stresses. Okay, and these planes are called as principal planes. This is the definition of principal plane. Okay, where no shear stresses are present after resolving all the stresses where no shear stress is present, such planes are called as principal planes, and these planes are three planes and which are mutually perpendicular to each other. Okay, and the stresses that are on these planes are called as principal stresses. Okay, now let us find out how these principal stresses are mathematically found out. Okay, the plane of which the maximum shear stress acts are known as plane of maximum shear. See, now you remember there are principal planes in which shear stress is zero, and there is another another plane which is mutually perpendicular to these two, which is called as plane of maximum shear. Okay, there in that only shear force will be there, and no um, direct stresses will be there. Okay, you see here this oblique plane is given like this. I don't know. Okay, actually, no, we need not go deep into this. You need not even draw this diagram when they are asking about principal stresses. You see, and just you say what is the principal plane and what is the principal stress, and then how the principal stresses are given mathematically. Okay, and now maximum principal stress is given as sigma T1. See, T stands for tensile. See, the principal stresses is tensile stresses. Uh, Okay, sigma T1. This is the maximum is called 1 and minimum is called as 2. So sigma T1 is sigma 1 plus sigma 2 upon 2. That is sigma 1 is uh, 1 direct stress. Sigma 2 is the direct stress mutually perpendicular by 2. That is in this plane you can see. This is sigma 1, these two, and these two are sigma 2, and this is the third one, tau. These things are tau. Okay, so this is the formula. Sigma 1 plus sigma 2 by 2 plus half of square root of sigma 1 square minus sigma 2 square plus 4 tau square. This is the maximum principal stress formula. This formula you should remember. As a how it is derived, that is out of the scope of this course. We are not going to derive it, and nobody is going to ask how you have derived it. Only you remember. Actually, you should have learnt it in strength of materials or applied mechanics. Okay, minimum principal stress is again sigma T2 is equal to sigma 1 plus sigma 2 by 2. Here the terms are same, only that up there is plus and down there is minus. Okay, and then the plane of maximum shear stress are at right angles to each other and are inclined at 45 degrees to the principal plane. Oh, so it is inclined at 45 degrees, not 90 degrees, as I said before. Okay, so see the maximum principal stresses are inclined at 45 degrees, and um, the maximum shear stress is inclined at 45 degrees. Maximum principal stresses are inclined at 90 degrees to each other, and this is inclined at 45 degrees. And the formula is given like this: maximum shear stress is sigma 1 minus sigma 2 upon 2, that is uh, that is equal to half of square root of uh, that is half of square root of sigma 1 minus sigma 2 square plus 4 tau square. Actually, this is the same term that is here, here and here. So these are the three formulae you have to remember. Sigma T1 is equal to sigma 1 plus sigma 2 by 2, whereas plus half of square root of sigma 1 minus sigma 2 square plus 4 tau square. The second term also is same, only that here minus has come, and the maximum shear stress is this term we are not using, only this term half of square root of sigma 1 minus sigma 2 square plus 4 tau square. And to find out the theta, this formula is there, 2 tan 2 theta is 2 tau upon sigma 1 minus sigma 2. Okay, so these are the formulae. See, if principal stresses are asked, you have to say what are the principal stresses, what are the principal planes you have to first mention, and then what are the principal stresses, and what are those formulae that we use. You see, again I'll tell you in short. You see, what are the principal stress? When there are on a machine component, there are not only um, uh, not only direct stresses, but sometimes um, bending moments and shear stresses, torsional shear stresses, so many other stresses may be coming. So when all these forces stresses are resolved, so we find that there are certain planes on which only the direct stresses are present. That means no shear stresses. No shear stresses, only direct stresses are there. Such a plane is called as plane of plane plane max ma, okay plane of maximum direct stress, or principal stress, maximum plane of maximum principal stress. Okay, and another one which is mutually perpendicular to that, it's called as plane of maximum minimum principal stress. Okay, these are the principal stresses, and there is an another plane which is inclined at 45 degrees to those principal planes, and this is called as plane of maximum shear stress. So, and on these planes, what stresses are coming? They are called as either maximum principal stress, minimum principal stress, or maximum shear stress. On the shear planes, maximum shear stress will come, and on the principal planes, maximum principal stresses will be coming. Okay, this much is about the